Hello. The main objective of this video is to show the two fluid dynamics equations when we are working for real fluids. Also, the objective is to introduce you to the effect of viscosity in the fluid's conduction. To be able to follow that video, you are expected to know about the continuity equation and Bernoulli equation for perfect fluids, that is, without considering viscosity. Then we will put the emphasis on that video on what the effects of viscosity are. To do that, we will define viscosity, and then we will go into the first example, which is the difference between laminar and turbulent flow, and we will finish by considering the head losses as a consequence of the viscosity consideration. To finish, we will go to the Bernoulli equation to see how it looks when we are working for real fluids, which means when taking into account the effects of viscosity. Let's start then by defining viscosity, which is somehow the friction force when we're working with fluids. If we consider that the fluid is moving like you see in this image, formed by layers, then the result of the movement is that viscosity is the friction in the relative displacement of the layers moving. The viscosity is represented by the viscosity coefficient, but we usually say only viscosity, and its units in the International System of Units are the Pascal per second, also known as the decapoise. Then, as I said at the beginning, the viscosity has two main effects on the fluid conduits. The first effect is the possibility of the production of the turbulent flow, and the second one is the energy loss. Let's start with this first consequence, the type of flow. When we consider these friction forces in the fluid, some vortices can be origined. Then the laminar flow occurs when the fluid is flowing in parallel layers, and in the opposite, the turbulent flow occurs when the particles doesn't, and they follow chaotic movements. You have a very clear representation here in the image. Then how do we know if a fluid is flowing under laminar or turbulent flow? By using this experimental formula that Reynolds developed, and this is called the number of Reynolds, which is a function of velocity, density, diameter of the pipe, and inversely related to the viscosity. If all these magnitudes are in the International System of Units, then the number of Reynolds has no dimensions, and this is the critical value for the turbulence to start, which means if the number of Reynolds is higher than 2,400, then the flow is turbulent. Once we have seen this first consequence of the viscosity, the origin of vortices, now we're going to see the second one, which is the head loss or pressure loss. Let's see this drawing first. If this is a tank and this is a conduction, that L1 here on top would be the headline for an ideal fluid or a perfect fluid, which means there are no losses of energy, so the head is constant for all points. What happens if we consider now the effect of viscosity? Then let's have a look at this line L2, which represents the headline for a real fluid, which means when we have energy losses or head losses. On the other hand, this line 3 represents the piezometric line, which is the line representing the height of the water in the different piezometers. Again, if this was a perfect fluid, that line would be horizontal. Considering a real fluid, this line is not horizontal but decreasing. Let's see how can we calculate that energy loss in a perfect fluid. We have a law developed by Pascal some time ago, which gives us this expression for the pressure loss as a function of viscosity, the length traveled by the water, the flow, and pi r to the fourth. This is the way to calculate the pressure loss expressed in pascals when all these magnitudes are in the international system. And we can change also to the units of head, as we do always when changing from pressure to head, we multiply or divide by density gravity. So the pressure loss is density gravity times the head loss. So knowing that formula, we can divide by density gravity and then obtain the head loss very easily. This leads us to a very important concept, which is the use of bombs in conduits. Why? Because if we are losing energy because of the effect of viscosity, then probably we will need some bombs placed in the conductions to increase the energy of the water. The main characteristic of the bomb is its power, which is given in watts in the international system, and the power of the bomb is increasing the pressure or the head by following this expression. Power equals the flow times the increment in pressure, or the flow times the product density gravity and the increment on the head. This makes the water to be able to arrive higher than the initial height it was having, and also to compensate the energy losses due to the viscosity. So finally, when we consider the effect of viscosity and the possibility of having a bomb in a circuit, what happens with the Bernoulli equation? The Bernoulli equation came from the conservation of energy, from an energy balance. So we have to write the energy balance, as you see here, considering the energy of one point, the energy of the second point, but adding the extra energy given by the bomb, and adding at the second part the energy loss. Then, if we divide this energy expression into the volume, we are going to arrive to this, which is the most familiar way to write the Bernoulli equation in terms of pressure. So notice, this is the three terms of the Bernoulli equation: velocity, height, and pressure, plus the extra pressure given by the bomb. So this equals the three terms of the Bernoulli equation in the second point. Again, velocity, height, and pressure, plus this pressure loss between point 1 and point 2. And we can use Bernoulli equation written that way, or also written that way below, which is the one expressed in terms of head instead of being in terms of pressure. So let me sum up about what the effects of viscosity are in a fluid. First of all, we have to calculate the number of Reynolds to be sure that the flow is laminar and not turbulent, no vortices generated in the fluid. And after that, the viscosity makes that the energy is lost, part of the energy is lost, so then the Bernoulli equation has to be corrected from the one we had for the perfect fluids to arrive to this expression where a bomb is included. If we have a bomb in the conduit, that is, and we have here the pressure losses summed at the end. Thank you.